So this is the review for the test on matter and atomic structure. This is the first part of Unit 2 that we're going to have a test on. We'll have a second test on radiation, nuclear stability, and nuclear decay. So classify these as either physical or chemical changes. Well, tearing a piece of paper, anytime you tear, crumple, crush, grind, anything like that, that is a physical change. Okay, physical because you just have two pieces of paper, you haven't turned the paper into anything else. Burning a candle, anytime you burn anything or rust anything, that's going to be a chemical change. Boiling water, changes of phase or state, so solid to liquid, liquid to gas, or any combination of those two things, is always a physical change. When you boil water, you get steam, which is just vapor made of water. You haven't changed the water into something else. Copper tarnishing, that's a chemical change. It's like rusting almost. Tarnish is a chemical process where copper interacts with the air and produces another substance. And chopping wood, again, you're just splitting the wood into pieces. You're not turning the wood into charcoal or anything else, so that's a physical change. All right, take a look at these substances or mixtures and apply the letters to anything that is appropriate below. So which ones contain only molecules? Well, A contains only molecules, even though these little molecules are made of one element. Anytime you have two or more atoms that are bonded, that's a molecule. So A, and also C in this case, because these are all molecules and they happen to all be the same. So A and C would go there. Which is a mixture? Well, A is a mixture of this compound and this element, and B is a mixture of two elements. C is not a mixture because it only contains one thing. Which of these contains two pure elements? The only choice here is B, because both A and C include compounds. Which is a pure substance? Well, A and B are both mixtures, so that means only C is a pure substance because it's all made of the same compound. Pure substance doesn't have to be just an element. It could be a compound as long as it's all the same. And which of these contains no molecules? Well, A and C both have molecules. B is the only one that is not made of any molecules. They're all individual atoms. Even though it's a mixture, there are no molecules involved. Which of these is a pure substance? You have to remember a pure substance means it is either an element or a compound, and a compound is two or more elements that are chemically combined that cannot be separated physically, and they exist in the same proportions everywhere you find them, the same composition. So iced coffee, depending on how you like your iced coffee, there's lots of different stuff you can put in there. Salad is obviously made of different components that are mixed together. Soil, the same thing. Dirt, roots, animals, insects, things like that. Water, however, is a combination of hydrogen and oxygen. It is always two hydrogens, one oxygen, H2O, no matter where it comes from. So that's a pure substance. It's a compound. The other option for a pure substance would be an element like chlorine or gold. Those are all pure substances as well. How you differentiate heterogeneous from homogeneous mixtures? Well, kind of just talked about this in the last problem as well, but in a heterogeneous mixture, the individual pieces are not uniform, but they're also distinct, so you can sort of pick out the different parts of a heterogeneous mixture, like the different types of food in a salad, the rock and the roots and things in the soil, such as that. A homogeneous mixture, you cannot tell the individual components apart. Things like metal alloys, the air around us, salt dissolved in water, these are things where you can't point to one part of it and say, there's the salt. in the water. You can't see it anymore because it's so evenly mixed in with the water. Who developed the plum pudding model? You need to know what the plum pudding model is. It was developed by Thomson, and it looks something like this. You have this view of an atom with this vague mass of positively charged matter. Interspersed in there are these little negative things called electrons. So those are the plums in the pudding of this model. Okay, so it's this big mass of positively charged matter, not protons because they didn't know those existed yet, but just sort of a cloud of positively charged material with electrons inside. That's the plum pudding model that was developed by Thomson. Okay, you need to know that Thomson was involved in the cathode ray tubes. You need to know Milliken, oil drop experiment. Rutherford, gold foil, and he came up with the nuclear model. Dalton was early atomic theory. Okay, so you need to know what each of these people contributed to our idea of what atoms look like. Which type of elements make up the majority of the periodic table? Well, most elements, like 2/3, 3/4 of the elements on the periodic table are all metals. Burning a piece of paper, physical or chemical change. Okay, burning, again, anytime you see the word burning or combustion, you're talking chemical. You're combining substances with oxygen. That's what burning is. So it's chemical because it produces new substances. Okay, you do not get the paper back after it's burned. The key distinction between chemical and physical is that a chemical process produces new substances, whereas physical, like melting, you don't get anything new, it's just a different state. It goes from solid to liquid. Define an element. An element is a pure substance made of only one type of atom that cannot be separated by normal chemical or physical means. Pure substance of only one atom. Now that doesn't mean it doesn't have molecules, because some elements combine into what are called diatomic molecules, like oxygen and hydrogen and chlorine. One atom, that should say. And they can, I'm summarizing here what I'm writing because it would take too long otherwise, but cannot be separated. Okay, it's a pure substance of only one type of atom that cannot be separated by physical or chemical means. Location, mass, and charges of the three basic subatomic particles. Electron is negative and exists outside the nucleus. Protons are positive, neutrons are neutral, and these two exist in the nucleus. Electrons have no mass, or very little mass that we don't even count. Protons have a mass of 1 atomic mass unit, and neutrons also have a mass of 1 atomic mass unit. Which portions of Dalton's atomic theory have since been proven incorrect? Well, Dalton suggested that elements were made of tiny, indestructible, indivisible atoms. Okay, we now know, we learned after that indivisible is not true. Okay, atoms can be broken up into smaller pieces, protons, neutrons, and electrons. He also said that all atoms of every element were identical. Okay, they're not identical. We have isotopes. Isotopes are atoms of the same element that have different masses. Okay, so isotopes is the proof that not all elements are identical, and subatomic particles prove that atoms are not indivisible. The other things he said were that they combine in different ratios to form compounds, and that chemical reactions are just rearranging atoms. That's all true, but it was just these 2 points about atoms being indivisible and all atoms of the same element being identical that were later proven to be false. Okay, again, I mentioned this earlier. You need to know all of these things. What happened in Thomson's cathode ray tube experiment? What did that discover? It's the electron. How did they discover it? Rutherford's gold foil experiment, he fired the alpha particles at gold foil, and some of them bounced back, which suggested that the plum pudding model of the atom was incorrect. led him to come up with the nuclear model of the atom. Milliken's oil drop experiment, he used fine mists of oil and electrical charges to determine the mass of an electron, and that thus proved that electrons were much, much smaller than atoms. Thomson's plum pudding model showed you earlier. Rutherford's nuclear model has these protons in the middle and electrons orbiting around like planets. Okay, dense, positively charged nucleus, small electrons floating around in outer space. That was the result of his gold foil experiment. Okay, lead has 4 isotopes that have the following masses: 204, 207, 206, and 208. And the percentage abundance of each one is given. And this should say lead at the end. It's just a typo. What is the average atomic mass of lead? Well, to find the average atomic mass, you take the mass of each isotope, 204, 207, 206, and 208, and you multiply it by its percent divided by 100. So 0.014 for 1.4% times 0.221 times 0.241 and times 0.524. So those are all the percentages just divided by 100. Then we get what's called the mass contribution for each isotope. So the first one contributes 2.856, the second one contributes 45.747, the third one 49.646, and then the last one is 108.992. So you add those all up and you get a mass of 207.241. Now, that's not closest to 208, which is the most abundant isotope, but it is closer to 208 than it is 204 or 206. So it does get pulled up toward the higher end of the average than if you just added 204, 207, 206, 208 and divided them. If you did that, you would get 206.5. So this is much closer to 208 than it is to the actual average if you just took a straight average of those things. Okay, if you have 2 naturally occurring isotopes of lithium and you know that the average atomic mass is 6.941, calculate the percentage that is lithium-7. How do you do this? Well, we just went through how to find the average atomic mass. Now we're working backwards. So here's what we know. We know that we have to have 2 percentages that add up to 100% because there's only 2 isotopes. So the combination of those 2 isotopes has to be all the atoms, 100%. And we know that if we multiply the mass of the first one times, and then add that to the mass of the second one times its percentage, then all of that comes out to 6.941. Right? The mass of the first isotope times its percentage, we're going to call that X. That's the percent abundance. Plus the mass of the second isotope times its percentage adds up to 6.941. So if we solve this, we distribute the 7, we get 6x plus 7x minus, this should be 1 minus x. 1 minus x, that's what's confusing here. Okay, so 7 minus 7x equals 6.941. So, when you sort of resolve this over here, you end up with 7 minus x equals 6.941, which means that x equals 0.059. If you convert 0.059 to a percentage, that tells you that isotope 6 is 5.9% and isotope 7 is 94.1%. And that would make sense, since the average atomic mass is much closer to 7, that it should be the majority of the isotopes. Last one, filling in the table here. Okay, you have to sort of work with what you've got to find what you're missing. So atomic number 19 tells me that there are 19 protons, and if I look up number 19 on the periodic table, that's potassium. The mass number is the protons plus the neutrons, which in this case comes out to 51. Uranium, I'm only given the mass, but if I look up uranium on the periodic table, it's got 92 protons because it's atomic number 92, and then I just take 235 minus 92, and I find that that particular isotope has 143 neutrons. So take a look at these. Make sure you go over the experiments, the gold foil, the oil drop, and the cathode ray, as well as the plum pudding model and the nuclear model of the atom, that you have those down. Make sure you know how to find the average atomic mass, identify the different subatomic particles, protons, neutrons, electrons, atomic number, mass number, like we just did here, and you know mixtures versus substances, chemical versus physical. All those things, the questions that we just saw on here, are going to be just like the questions that you're going to see on the test.